Hello everybody, welcome to today's webinar. My name is Jamie Clayton. I'm the Operations Director at Freeman Technology, which is part of the Micromeritics family, and my job is moderating today's session. Really appreciate you joining and taking the time to listen to today's presentation. Hope that you find it interesting and valuable. Before we get started, just some quick guidance on the format for the event. You will notice that you're all in mute mode or listen only mode. So if you do have any questions that you'd like to raise, you can click on the speech bubble or the question mark icon, which is in the GoToWebinar dashboard on the right-hand side of your screen. And at the end of the presentation, we will have some opportunity to address some of those questions. Please note that when you do send a question in, it's only visible to organisers. All of the attendees don't see those. And if you do raise a question that we don't get a chance to answer today, one of our team will come back to you in the coming days and do their best to address that for you. Just so you're aware as well, today's event will be recorded and that will be available via the GoToWebinar page later in the future, and we'll send links out to everybody so that you can watch that again at your leisure or share with colleagues at any point in the future. So on to today's event. As you may be aware, we've been running a series of webinars over recent weeks. If you have already joined some, that's great. Thank you for joining. I hope they've been valuable and that you've enjoyed those. And we hope to welcome you all to future events as well. What we've had amongst some of the recent presentations is that we've been very fortunate to welcome some experienced guest speakers from industry. And they don't come much more experienced than today's speaker, who is David Smith from DJS Process Consulting. So I know that David plans to give you a bit more detail himself on his background and his experience, so I won't dwell too long on that, but I was lucky enough to first work with David probably many years ago than I care to remember, during his time at P&G, where he was heavily involved with product development and in particular scale-up work and process optimization. Since then, he's now gone on to set up DJS Process Consulting, where he's able to take a lot of that experience from Procter & Gamble and apply it to various powder handling industries throughout the world and in different sectors. So David's going to share with you today some of his experiences, particularly focusing on the need to turn the art of powder flow into a science. And on that note, I will hand over to David.
Hi everyone, I'm Dave Smith from DJS Process Consulting, and welcome to this online webinar on powder flow, and more importantly, when it doesn't flow. I'm pleased to have been asked by Freeman Technology to share my experience from a career in industry, and more recently in consulting, concerning all things powders, an industrial perspective on the need to turn art into science. I'd like to share my experiences in 5 sections. To start with a brief introduction to myself and my consultancy company. Then some opening thoughts on my experience working in industry, with a story about my first visit to a solids handling plant as a recently graduated engineer, and some observations from my 30 years of playing with powders in full-scale processes. Moving on to talk my personal perspective on industrial bulk powder handling challenges. Next, I would like to talk new challenges I see linked to complex formulated powder products. And finally, my closing thoughts on what the future holds. I studied chemical engineering at the University of Birmingham and graduated in 1987. I had plans to make a career in the traditional area of oil and gas, but almost by chance I became aware of careers at Procter & Gamble. I was attracted to their approach of putting new graduates on real projects from day one, and I went straight into P&G after completing my degree. It proved to be a good choice, and I enjoyed a very varied and exciting career in Procter & Gamble for almost 29 years. I was fortunate to be involved in projects from early stage innovation through to detailed plant design and commissioning. Having enjoyed doing some internal consulting within the large global P&G empire, I took a decision to leave and form my own company in 2016. As just mentioned, my career history was very much focused on taking early innovation through to profitable manufacturing reality, and this is our main aim in DJS Process Consulting. To complement the consultancy services, we also support detailed engineering design with the latest 3D virtual reality engineering software from Autodesk, and a team of experienced engineers covering all process scale-up activities from drawing P&IDs to on-site commissioning support. Having started alone in 2016, we're now a core team of 8 consultants with a global client list supporting products as diverse as cat litter to ceramic tiles. I'd like to kick off with a totally true story of an early experience in a manufacturing site on my first project. This involved a plant in France to which a team of 5 of us had travelled from the UK-based process development department. The objective was to run granulation trials on a continuous process based on only a few kilo scale batch experiments. The product was a respiratory hazard and therefore necessary to wear air-fed helmets. As the most junior member of the team, I was assigned to the bulk bag station to wait the flow of product and take samples. I will never forget the experience, since there was no means of communication, and I stood at my station for about 4 hours waiting for the good product that never arrived. Why? Well, the sticky agglomerates produced in the granulation step was simply too sticky to be handled in the fluidized bed dryer, and every attempt failed, resulting in a lengthy manual dig out of the dryer. On the upside, this project was my first very enjoyable exposure to French cuisine. Moving on to 2 examples where the powder flow properties are not matched to the equipment. The bottom of a dust filter on the top of a powder processing plant, and a heavily hammered small hopper at the head of a powder packing line. Both problems related to an engineering design failure to account for different climatic conditions. Both examples are in India and subject to hot, humid monsoon conditions. It still continues to amaze me when I see expensive solids handling equipment designed only according to previous best practice, without any attempt to properly understand the material the equipment is meant to handle. It's a bit like an engineer in an oil refinery buying a pump without any consideration of viscosity. Yet, it still happens all too often. It is unfortunately true that powders don't have a simple equivalent to viscosity, but that doesn't excuse the situation. At best, the end result is pain for the operators and some downtime. At worst, these problems can make a process uneconomic to operate. In this example, a lack of experimental understanding at small scale on the impact of the level of liquid addition on dustiness when coupled with the more complex conditions in production equipment compared to the lab. This is a batch spraying drum for the addition of liquid levels up to around 10%. I think the lab scale experiment was done in a food mixer. However, at large scale there are many other factors coming into play. If I recall correctly on this example, the key problem was spray flux. The liquid was being added too quickly and focused over a small area, too high a flux. The solution was more properly sized spray nozzles spread over the length of the drum. You can see that the first mistake was not a pleasant experience for the forklift driver when the batch was discharged. Correcting the spray flux resulted in a non-dusty product as produced at lab scale. And my last example illustrates multiple issues, but the resilience of the operator reminds me that it is our job as engineers to design plants that are safe and easy to operate. This video could be used in a health and safety exam. You can clearly see lack of dust masks and an acceptance that it's okay to continue with the obviously unsafe condition. The root cause in this example was down to poor maintenance. Seemingly minor but critical components such as flexible connections between equipment were damaged, and the management culture in this plant allowed these conditions to remain. You may wonder why I made the opening comment about plant design, since this was a maintenance issue. Well, I'd like to use this example to make the point that detail is important. So in this example, the choice of flexible connections was left to the installation team, who not surprisingly installed cheap homemade cloth type flexibles. Robust flexible connections are available for powder plants, but the design team must have felt that this level of detail was unimportant, so they left it to chance. In my experience on powders, specify everything if you want a safe and reliable plant. To sum up my feelings from my early years in industry, a total lack of interest or belief by senior management in the point of doing any small scale experiments to predict the large scale. In defence of my senior managers, there was a serious deficiency in characterization methods for critical quality parameters on solids, generally just simple hand operated tests that have been used for many years. As a process development engineer in a global FMCG company, I quickly realised that process scale-up was going to involve lots of travel, since management wanted the full-scale confidence on new projects before committing to launch. This approach worked if you had large-scale equipment already in place, but was a disaster for project costs, although good for frequent flyer miles. I also realised the remarkable resilience of process operators to deal with poorly designed equipment, and finally, this looked like a good career choice for lots of challenges and excitement. Moving on, I'd like to share my personal observations on the evolution of bulk powder flow measurement techniques from the early 90s to the present. When I started in industry, powder flow was mainly assessed by an unreliable cake strength test or simple pour test. This was part of the problem driving senior management insistence that all changes had to be tested in the plant. In the next few slides I'll talk early attempts to introduce better methods, introduction of the Peschel test, and more recently introduction of the Freeman FT4. The baseline was the so-called cake strength test or unconfined yield strength, but typically done by hand, thereby introducing lots of variability. A well-intentioned senior technical manager arranged the purchase of a Yenneker shear cell. In an industrial environment, it wasn't possible to dedicate a full-time technician, leading to unreliable results, plus no one really knew how to interpret the data except for hopper design. This wasn't the main interest, since new hoppers weren't installed that often. The interest was in more complex problems of flowability in process equipment such as packing machines. The equipment was only used for a few years and was eventually donated to a university. In the early 90s, I was working on a project where we needed to know how much to dry a new agglomerate so that it would flow okay through existing silos. This was a critical question, since over-drying would cost more in capital investment and running costs, plus the material would be more friable, which was undesirable. We needed an accurate flow test that would allow the identification of an operating window, which would enable the design of the fluidized bed dryer to robustly provide material with good flow winter and summer, without being over-dried, wasting money and potentially impacting product quality. The Peschel test was identified, and due to its operation being semi-automatic, it produced a generally reliable output. We used the Peschel test to measure pilot plant product and successfully identified an operating window which worked when we built the full-scale plant. The Peschel was used for many years until becoming obsolete. Its capabilities were, however, limited purely to silo design, so it was unable to help with a host of other powder flow related questions. Support for the Peschel test was discontinued, and P&G was looking for powder flow characterization tests with wider capabilities. I was introduced to the Freeman FT4 in 2010. It was deployed to replace the Peschel test, but with many broader options. Like the Peschel, its operation is mainly automatic, but with a vastly superior user interface and built-in features such as linking your shear cell data to silo design parameters. The range of available tests extends far beyond simple shear cell testing. And whilst not all the tests have strong relationships to scale-up parameters, the wider range of tests make it very useful to study many more problems linked to powder handling. It became well accepted in P&G and was deployed in most regions. The big challenge is still around linking these lab-scale measurements within process behaviour, beyond simple silo design. This can be done, but requires effort. For example, I developed a link between flow energy and powder dosing accuracy in a packing line, but much still remains to be done in this area. Now I'd like to move on to share my experiences on the solids handling challenges coming from complex formulated products. I will discuss first, what is a formulated product? Secondly, a personal example where I played a leading role in the process development and scale up to manufacturing. And finally, my thoughts on new technical directions in this area. So then, what is a formulated product? Quite simply, a product made of a mixture having a higher value than the sum of its parts. The added value coming from the expertise in putting together the formula. Common examples being detergents and foods, with less obvious examples such as crop protection granules for dissolving crop sprayer tanks or granules for lawn care. Top solids handling related problems coming with formulated products include dose consistency. The composition for every use should be exactly the same. It generally isn't due to segregation. This is very important for consumer satisfaction, which can drive critical success factors such as repurchase intent. Segregation could mean you only have one crouton in your cup of soup, or it could be low or too high bleach in your scoop of detergent. Either way, the product isn't as intended, and maybe you'll choose to buy another brand next time. Secondly, process capability to mix very low-level ingredients such as enzymes in detergents. The composition of formulated products is highly tuned to balance performance and cost. Some highly active ingredients only need to be added at a few %. The ability to well mix low-level ingredients and to prevent demixing or segregation can be quite a significant challenge. And finally, filling accuracy in packing to minimise giveaway. In all countries there is legislation on pack weights to ensure consumers aren't shortchanged. If you sell a 1 kilo pack, the batch average must be at least 1 kilo. Clearly this means you must on average slightly fill more than 1 kilo to be safe. The difference is giveaway, so called because it's above what you plan to give the consumer and caused by variability in your packing process. If you had a perfect pack filling process, giveaway could be zero. And giveaway can amount to millions per year on big volume products. In packing, process engineers put a lot of effort into minimizing giveaway. I know, I spent quite a lot of time in this area myself trying to make products inherently easier to fill with less variability. I'd like to discuss a personal example when I was involved in the process development for Cascade Action Packs, a US unit dose auto dishwashing product. This was a unique new product consisting of separate powder and liquid compartments contained within water-soluble film. In an attempt to save costs, the engineering team developed in-house a very simple powder dosing concept consisting of a fixed volume container with simple upper and lower slide gate valves. The concept was built and failed due to bulk density variations causing unacceptably high weight variation from pack to pack. For me, this was a classic example of not understanding process requirements before diving into equipment selection. The team developing the slide gate concept knew that the requirement was to fill by weight, but they devised a concept that fills by volume with no adjustability. Basically, they had assumed that the product bulk density would be constant. In a complex mixture of more than 10 materials, this is certainly not the case, and the weight variation was simply mirroring the density variations of the feed. The solution was a vertical auger doser, which had the capability to accurately adjust the dose-to-dose volume by volume. This is still a volumetric concept, but critically it can be adjusted whilst running. This enabled a feedback control approach which delivered the desired pack-to-pack weight control. Now, I'd like to share my experiences on how many companies are reaching out externally to build knowledge and solve problems. Procter & Gamble calls this connect and develop. Many large multinationals have historically been very secretive and prefer to handle all development in-house. This is changing. Before I left P&G, I was involved in a significant shift towards external collaboration. One good example is the UK Engineering Doctorate Programme. EngDocs allow industry to directly influence PhD level research to be very focused and relevant to industrial needs. I was a supervisor for one EngDoc which was focused on powder buildup in auger fillers. These are extremely common devices handling materials ranging from detergents to foods. In the previous slide, I explained how this type of equipment was successfully deployed to fill powder in the Cascade Action Packs product. One problem in laundry detergents is that due to the typically high organic component of the formulation, the powder can be quite sticky. This can lead to product buildup in the auger and frequent downtimes for cleaning. Compared to traditional PhDs, the EngDoc program allows high focus on specific industrial problems, in this case understanding what causes powder buildup in auger fillers. The project was a success and developed understanding which we were able to directly apply in the laundry powder packing lines to solve build-up problems. The picture shows a cutaway of an auger filler internals, and the video is an example of an auger filler dosing powder into bags on a rotary filling head. To close with my thoughts for the future, how do we achieve this lighthouse vision to link easily measured powder properties to process plant design and operation? The link between material properties and process conditions being the key point. A process makes a product, and the challenge is to link meaningful product quality measures, such as bulk density, to the process levers. I will come to this in my next slide. Industrially relevant measurement systems for solids are becoming much more prevalent. We need to deploy them, use the data they produce, and accept that we can all play a role in furthering our understanding. A critical factor driving change is that, in my experience, senior management will no longer accept or fund lengthy startups on solids plants, thus driving the focus to small-scale understanding. And finally, we can benefit from vastly superior capabilities in the collection and manipulation of process data, coupled with new inline measurement techniques such as the Lantera probe for powder flow. This is key to drive the necessary depth of understanding. In a typical powder processing plant for formulated products, the packing area accounts for at least half of the plant footprint and often at least equal capital investment. Packing is a critical area for both cost and consumer satisfaction. In the bulk making side of the plant, the product will be produced to match strict quality limits. However, this effort can be wasted if the quality of the product in every pack is not the same. Factors such as segregation and particle attrition can lead to unexpected quality problems with the product actually leaving the factory for consumers. In addition, money can be lost if the packs have to be overfilled to respect minimum fill regulations due to poor dosing control. The area of powder packing is a major gap both within industry and in research centres, where I'm not aware of any setups aimed at developing deep understanding of powder processes at industrially relevant scale. I was privileged to be involved in developing such a facility at the Centre for Process Innovation, which enables the study of multiple powder processing unit ops linked to packing. Plus, this is coupled with state-of-the-art online instrumentation for both process parameters and product quality attributes, also complemented by an impressive powders lab. This slide is to give a snapshot of the type of instruments available on the CPI test rig. The rig is controlled by a PLC with a large screen user interface for easy control and real-time viewing of parameters. The heart of the data acquisition system is two rack-mounted industrial PCs, which interact with a host of advanced online analytical instruments, together with all process conditions such as flow rates, motor speeds, temperatures, etc. The online analytical instruments provide information on product composition via spectroscopy, particle shape and size via advanced image analysis techniques, and bulk density by low-level radiation. This type of rig, coupled with offline measurements, will drive the required depth of understanding to achieve my lighthouse vision. Please feel free to get in touch with me if you're interested in accessing this facility based at CPI in the northeast of England. So, the technical capability is becoming available, but what more is needed to make real progress? A belief by decision makers that is worth the effort. Speed and cost are the best arguments. It is well documented that startups of solids processing plants run way over budget and schedule far more often than fluids-based plants. Startup delays can easily run into millions in costs, plus knock-on effects such as, for example, missed launch timings. Secondly, a passion for data collection. When I started out in industry, I was recording data in a notebook. Thankfully, those days are long gone, but I'm still surprised all too often by the lack of interest in the data that is typically available from a modern PLC-controlled process plant. Why? Well, the problem seems to be a combination of stretched engineering resources in most plants, coupled with the fact that extracting the data is not intuitive. This is actually an area where my company offers solutions to add user-friendly front-end interfaces on top of existing plant data systems to make data extraction and analysis as easy as ordering something off Amazon. And finally, speaking from an industrial perspective, we need pragmatic solutions. Where currently in solids processing, little predictability exists, except perhaps for silo design. Industry wants simple answers. It is the very complex nature of solids that first principle-based approaches have to be blended with empirical and big data approaches to provide the answers needed by industry. To close, I'd like to say a few more words about what we do at DJS Process Consulting. Our mission is to partner with our clients to help them achieve their business objectives by leveraging the technical, project management and business leadership skills available via our team of experienced consultants. Typically, we partner with our clients and projects and work alongside client employees to achieve project deliverables. We have a core set of 3 areas of service. Firstly, consultancy. Core areas of expertise cover the full remit of R&D activities in formulated products, with a strong focus on product and process development, intellectual property development, scale-up and process optimization. Secondly, engineering design and project management. DJS Process Consulting can provide fully outsourced engineering and project management services. These include development of process flow sheets and P&IDs, full 3D and virtual reality CAD plant layouts, equipment and electrical specifications, quotation and vendor management, and overall project management. And finally, the intelligent manufacturing, or IMP as we call it, hardware, software and remote technical support for your production lines. Here at DJS Process Consulting, we see a trend towards lowering of staffing of experienced level engineering support people in manufacturing facilities for FMCG and other products. Gone are the days when every production line would have a dedicated process engineer. We have the skills to remotely support your manufacturing sites with the type of issues traditionally handled by on-site, highly paid graduate level engineers. If your process data is not historianized in a secure, remotely accessible way, we can also provide low-cost hardware and software to securely store your process data so that it can be accessed by our experts to support your production staff. Thank you for listening. I hope it's been interesting and thought-provoking. Here are a few clients of DJS Process Consulting, some household names and some companies you've probably never heard of. But I'd just like to mention a couple since they illustrate the amazing broad importance of solids processing and a kick for me personally in how my knowledge originally built on washing powder is now being applied to such a broad range of products. VCore, which is a green ceramic tiles company incorporating fly ash into their product. Agri Naturalis, who are producing a natural granulated form of pesticide. And Bioconservation, who make a spheronized food preservative for long sea shipping in containers. And to close, I think we have some time left for questions. Thank you.
Thank you, David. Thanks for a great presentation. Bear with me while I just transfer things back to my control. It's always great to hear about your experiences in different industries, and in particular, I always enjoy hearing the real world applications of what typically starts in an R&D lab. So thanks again for a great presentation. One of the comments that the comments that you made towards the end there is always something I found critical during my time in this industrial arena, and that's how much we can learn from other industries. You mentioned there that what you've learned from handling washing powder and detergent capsules has been relevant to manufacturing tiles and agricultural products. And I always think it's interesting that, ultimately, whilst you go from industry to industry and sector to sector, the scales may change, the terminologies may change, but physics is physics, and the same factors that dictate filling a tablet die can contribute to detergent boxes or filling bags of cement or anything really. So it's always interesting to hear that you've shared that same experience as well. So as you can imagine, we've had quite a few questions come in. I've got a handful that are very similar to each other, so I'm trying to put those into a question that you can handle, David. But the first one here is, what are the big challenges, in your opinion, for linking process parameters to real-time product quality attributes in powder processes?
Thanks. Yeah, I'm glad that question came up because it's an area that I feel a lot of passion for. I just going back to my story of my first experience in a plant in France. If I may just add that after that first 4 hours in standing at the big bag station waiting for nothing to arrive, yeah, as I mentioned, we had a very nice meal that evening in a French restaurant. But the next day was really the start of my journey and my own passion to try and use data to understand more about powder processes. But yeah, to answer your specific question, the biggest problem for me, firstly, is a lack of online measures for quality parameters for powders. And I stress online as opposed to at-line. So online does exist, and I've got personal direct experience of in playing around and implementing online measures for moisture, particle size, and density. And you know, this equipment does exist. In my experience, it's always failed in a real life manufacturing environment, and that's due to two key reasons. Firstly, the equipment typically requires frequent calibration, recalibration, and also frequent maintenance. And this sort of kit in powders, it tends to work when you have a dedicated resource or the external, you know, engineers or R&D who are passionate about it. They can keep it in tip-top condition and it works. But then as soon as you hand over to manufacturing, and know anybody online from manufacturing, I have a great disrespect for manufacturing, who you've seen my examples of what some operators have had to put up with. But in reality, in manufacturing, you're under a lot of pressures, and sometimes looking after highly tuned, delicate equipment, you know, it just falls off the radar screen. So that's the first aspect. And then the second point I would make is if we try to put in an equation what we're trying to do there, we're basically trying to create an equation of the form where product output measures, such as particle size distribution, is some function of process conditions. Now, what I see in industry which makes that difficult is that, partly linked to my first point about online systems, generally quality and process data is in separate databases, and that's because, as I've just said, there's very little success in true online measures. So quality is normally measured in a lab, and that means they're in different databases. Often the time that samples are taken isn't recorded, and the time of analysis is recorded. So you get offsets between the output data and the process data. So therefore that makes it really hard to develop relationships. And then my final reason, which actually links back to one of the videos, is that powder, unlike I'd say most fluid processes, which are generally contained because they're run often at high temperatures or high pressures or whatever, so they're largely independent of the surrounding environment, powder processes can be strongly influenced by factors that are not recorded. So my video of the guys hitting the bottom of a filter on top of the plant in India, that was linked to monsoon season. And throughout my career, I've had so many arguments with purse string holders about the need to have extra instrumentation to measure things like ambient temperature and relative humidity. And I think that video perfectly illustrates my point, that if you are trying to develop this linking of process parameters to real-time sort of outputs, you know, in that example in India, unless you recorded ambient conditions, you will be totally failing to develop that relationship. So yeah, that's my thoughts on that one.
Okay, I mean, probably another question we've had along very similar lines, and I guess this is going back a stage further, but linking the process parameters to product quality is one thing, but what are the challenges of linking the small scale material properties that are measured in the lab to the process parameters and then the product quality as well?
Yeah, Yeah, indeed. That's very much like a good follow-on from the first question. So in my experience, it is rare in powders to be able to scale up from theory. And by that I mean in classical chemical engineering, which, you know, as we all know, is very fluid based. We typically, as chemical engineers, or in our training as chemical engineers, we basically learn how to take measured small scale data of materials like viscosity or whatever, and how we use that with accepted theory to design full scale equipment. And that's really the perfect situation from a cost point of view, in that you can totally bypass pilot plant. Now in powders that is very rare. I just want to mention one exception that actually allows us to do that in powders, and it's close to my own heart because I've been involved in scaling up and designing and operating quite a number of continuous fluidized bed dryers, and it's, I think, a fairly rare exception in powders where you can actually do this for fluidized beds, because fortunately, down to people like Professor Derek Geldart, there's quite a lot of knowledge being gained in this area. And I think it's partly due to the fact that obviously by definition a fluidized bed behaves somewhat like a fluid. So things like drying curves, minimum fluidization velocities, these things measured at small scale can allow us to successfully design large equipment. And as I say, in my experience, I'm talking like 12-meter long vibrating fluidized beds that handle sort of upwards of up 50 tons per hour. But in terms of more generally, it is very challenging, and I'd say the fluid bed example is not one that repeats anywhere else in the powders world, with the exception of silo design, I should add, which obviously we all know is well understood.
Sure.
So what we need to do, in my experience, is typically look at two scales to get the confidence. And I'd like to just mention one area that I've got some experience in, which is bringing, shall we say, hope in this area, and that's discrete element modeling, DEM. I've got some experience of this on a number of projects, and it does really show a lot of promise to enable the use of fundamentally measured parameters of material properties to design full-scale equipment. The downside is, where it stands at the moment, is you typically need to validate the parameters. So I'll give one example. Coefficient of restitution is an input for DEM typically. Now that is something you can measure if your particle system was billiard balls, but if it's, you know, irregular shaped powders, you can't really measure that. So it's somewhat of an academic concept in real life, and the only way to validate the parameters in the model is to do some tests on full scale, or at least some scale of equipment, to validate your parameters. So that's the downside of DEM, in that you need some degree of validation before you can then test unknown conditions. But I do believe, Jamie, that DEM probably in the powders world is the most hopeful prospect, or shall we say, creating the equivalent that we have in fluids of using, you know, accepted theory, Bernoulli's equation and such like, to get powders to the same state as fluids.
Yeah, I think I would be inclined to agree with that. And interestingly, the next question I had planned was something along those lines, in terms of the development of first principles versus experience, and how that transitions into modeling and simulation of powders. And I agree with what you'd said there. I think I'd also add to that that just in my own experience, there's some very interesting work coming out of several universities on that front. The ones I'm mostly aware of are University of Leeds and University of Surrey in the UK,
Yeah,
that are doing a lot of work on modelling and simulation of powders under different stress and strain conditions. So yeah, that's another question that we've had there. One of Next question we've had is on one of the slides, you mentioned about finding a strong relationship between flow energy and dosing performance in one of your applications at P&G. Could you tell
Yeah,
us a little bit more about that, and in particular how then you went on to use that flow energy measurement to optimize that packing line and to monitor it going forward?
yeah, okay. So let me start by saying a few words of background perspective on packing in bulk consumer goods. So as I've mentioned in terms of this giveaway parameter, packing, so the way the product is sold is by weight, but you may be surprised to hear that most packing is actually done by volume. And that is quite simply because to fill powders into receptacles at speed, it is quite hard to do it by weight. Now, equipment does exist, but it typically can't go at the same production rates as by volumetric. The gravimetric machines, as they're called, always have to fill on what is called a bulk fill, which is quick, and then a fine fill, which is slow. It's a bit like if you're weighing something on a balance in the lab, you know, you chuck in quite quickly sort of 90% of the powder, then you slow down at the end to get the right amount. Now, on a lab, in the lab, that's quite easy. Time isn't so important, but on a production line, when you're trying to pack at hundreds of packs per minute, that can be a challenge. So most filling equipment is volumetric, but we still have to have an output of the overall process, which is by weight, and that's achieved by having check weighers and feedback control to the volumetric filling process. So in any feedback control loop, if the process that you are controlling is unstable, it makes that feedback control potentially impossible, or certainly more difficult. And what I found coming finally onto flow energy is that it was really the variability in flow energy for a given material, or indeed between different materials. So it wasn't just measuring one flow energy, it was more about looking on a given material, the variability in flow energy, and that was proportional to pack weight variability in the final packing line. So, you know, okay, you may say, so what did we do with it? Well, clearly we needed to reduce that variability in order to make the behavior of the product better. And the fact that we could put numbers to it, that's really what was helpful. So within a given product, we if you were looking at improving an existing product, then you don't normally want to change the formula. So on an existing product, we found things like the way, for example, maybe perfume was sprayed on. If that wasn't done in a very good way, and you got pockets of sticky material, that would then drive this variability in flow energy. So really, in that context, in terms of optimizing a process in an existing running, you know, currently in the factory, we were looking at how to tune process parameters to achieve less variability. And in the past, you know, we would just do that by trial and error. But now with the flow energy measurement, we had something that we could put really, you know, concrete numbers to the changes that we were making. And then just to close, if we were developing a new product, then we had the flexibility to change the formula. So we were able to play with the formulation to actually reduce variability in flow energy. And with that approach, this wasn't the only factor, but significant savings and improvements were made in giveaway, which, as I've said, on big volume products can account for millions per year in terms of cost or money that was essentially lost.
Okay, thanks, David. So just one question that's kind of relevant to that, which was asked earlier, and you can probably answer fairly quickly on to wrap that up, is that if there's a variation in bulk density, that obviously causes a variation in your dosing. So is there any effort made to control that bulk density, or is it just accepted that that's going to vary, and then the process equipment can be optimized to deal with that variation?
Yeah, well, clearly everything's interlinked. So flow energy isn't like standalone to bulk density. The two are somewhat linked. But yeah, bulk density is definitely controlled as far as possible. So in I was going to say in detergents, but broader detergents in agricultural products or in dried soups or whatever. Typically, there are two ways of making granules: spray drying or granulation, high shear granulation, similar to what is done in pharmaceuticals. And in both those processes, there is measurement and control of density. So in spray drying, for example, it's linked to the porosity of the particles, which can be adjusted with things like temperature, pressures, etc. In continuous granulation, or indeed batch granulation, things like binder level, residence time, etc., can control density. So absolutely, the best attempts are made to control it. But going back to my first question, one of the big challenges is it's not typically measured online. So you make changes to your process, and you only can see that change maybe, it takes a few minutes to take a sample, has to go to the lab, so sort of 30 minutes later you get an answer. If I may make an analogy, it's a bit like having cruise control on your car, but the speed, you don't have a speedometer, so you got somebody standing next to the car with a stopwatch, and that's how you get speed. So unfortunately, I think that analogy is unfortunately quite true, that when you can't measure much online in powders, it definitely makes all the control challenges very much harder.
Sure. Okay. And you touched on it there, and also in the presentation you gave the example of the single crouton in the soup. Segregation, what advice do you have, or any tips for managing, controlling, or even just measuring the impact of segregation?
Well, for measuring it, the best way is, if you want to assess segregation in an existing process like the croutons, is to quantify the thing that's of interest. So if you run a 2-hour batch of cup of soup production, you want to randomly sample or do a sampling of that production and literally count the number of croutons in every pack. That is absolutely the best way of doing it. And I've done this on commissioning of various processes, for example, dishwashing tablets, where there was concerns about segregation from batch to batch, and we simply had chemical analysis for surfactant and bleach and the key components done on multiple tablets, and we looked at variation. If you can't do that, if you've got a new product and you haven't built the process yet, there are some standard tests. The simplest one is to pour the material into a heap, and then to sample, from the center of the heap, the edge of the heap, etc., and look at variation. If a material has a low propensity to segregate, then obviously the composition from outside to inside is going to be very similar. In terms of, there's also a very good test called the spec tester, which was developed by Kerry Johansson. That's a very good equipment, because that basically is the heap test concept, but it uses spectroscopy to have a very neat automated way of analyzing the content of each slice. In terms of minimizing, you can tackle from the formula design and or the equipment. So classic ways of minimizing in the product are keeping particle sizes, particle shapes similar. Avoid, for example, cylindrical objects in a product that's where the rest of the things are little spheres. And if you can't do that, make it cohesive. More cohesive will minimize segregation. but can bring other in-process problems. And then really good equipment design. So I think probably most of the audience have heard of mass flow and funnel flow. So make sure your equipment is designed well and avoid the formation of heaps. So if at all possible, keep product moving in a consistent way. When levels change in hoppers, you're forming heaps. So if you have a hopper that is going to be filled and emptied, try to minimize the difference in levels between like the refill and the refill level and how high you fill it. Try to refill more frequently, because when you fill it, you form piles, and that is creating segregation. So yeah, I'd say it's equipment combination of those two factors, and you can massively reduce segregation even on a difficult to handle material compared to if you design the process without any consideration of the points I've just mentioned.
Sure. Okay, and probably time for one more question. A similar kind of vein, really, but now looking at caking. Somebody has asked what parameters, what properties would you measure of a powder to investigate propensity for caking, and how that might impact on flow behaviour?
Right. Well, caking was one of the first things I probably sort of started learning about in P&G, and as I mentioned from the beginning, it was a correct unconfined yield strength test that was used. Unfortunately, the cake was broken by hand. We literally had a drill stand that you can buy for, you know, a domestic drill that allows you to put the drill on a vertical axis. So you pulled a lever, so you broke the cake in an uncontrolled way, which gave very big variations in the result. So I'd say the unconfined yield stress done on, you know, a well designed reproducible piece of equipment is a very good approach. Obviously, all the classical shear cell work, looking at compression under different forces. So that's one thing that I've seen where people make mistakes, is that in companies, when a test is developed, like the cake strength test, as it's often called in industry, that has to be done at a certain consolidation force. And in industry, it's typically set at some force that's sort of appropriate to that company. But then when circumstances change, people forget that it's pointless doing a really high compression force if you're looking at low compression in a packing line, and vice versa. So I think, yeah, those are the tests I'd look at. I know we're about to run out of time, Jamie. That's what I'd focus on, but think carefully about how the test conditions linked to your process conditions.
Yeah, agreed. And to the couple of people that asked that question, I would just add as well that we have some really interesting application notes and case studies that we've undertaken on caking, and we can make sure that you get those in response to your question as well. So I think, as you say, David, that probably takes us up nicely to the end of our allocated time. There's a few questions we didn't get to, but rest assured our team will be in touch to answer those for you. And there's a few I've seen that are probably more relevant for David, so we'll pass those on and he can be in touch. So thank you all again for attending. When you leave, there will be a short survey. We would be really grateful if you can take a few moments to complete that, because it really helps us tailor future events. Any more information that you want on the Micromeritics range of products, you can visit our website. You can see there micromeritics.com or freemantech.co.uk if you're particularly interested in the FT4 powderometer that David introduced there. And if you're interested in learning more about DJS Process Consulting, you can contact David via david.smith@djsprocessconsulting.co.uk. So thank you again for your time, David. Much appreciated. Interesting as always. And thank you everybody for joining, and goodbye.
Thanks everyone. Bye.
Bye.